In this lecture, we're going to start getting into the nitty-gritty and the details of R. In particular, I'm going to talk about different data types that are used in R and some basic operations on those data types. So first, it's important to kind of get the language right correctly. So all the things that you manipulate in R, all things that we encounter in R, are what might be called objects. Objects can be all different kinds, can contain all different kinds of data, but everything in R is an object. So the R has five basic atomic classes of objects. So these are kind of the very low level or basic classes of objects. And they are character, numeric, so these are like real numbers or decimal numbers, integers, complex numbers, and logical. So logicals are just true-false type things. And so the most basic object in R is what's called a vector. And a vector can contain multiple copies of, for example, of a single type of object. So you can have a vector of characters or a vector of integers. One thing you cannot do with a standard vector is have mixed types of objects. So you cannot have a vector of characters and numerics, or numerics and integers, or integers and logicals. Everything in a vector has to be of the same class. Of course, with any great rule, there's always an exception, and this one is no exception. So in this, with vectors, there's one type of vector that can have multiple different types of classes, and that's called a list. So a list is represented as a vector, so it's a sequence of objects, but each element of that vector can be can be an object of a different class. So for example, you can have a list that has a character, it has a numeric, it has a logical. You can have a list that's inside the list. One element of the list can be a data frame. So any element of the list can be anything. And that's actually what makes the list so useful. So the list is one exception to the general rule that vectors can only contain elements of the same class. So you can create an empty vector with the vector function. And the vector function has two basic arguments. The first argument is the class of the object, so the type of object that you want to have in the vector. And the second argument is the length of the vector itself. Perhaps the most important type of object in R, of course, is the number. So numbers in R are generally treated as what are called numeric objects. So pretty much all numbers are treated as double precision real numbers. So even if you're looking at a number that's like 1 or 2, R thinks of those numbers as numeric objects. There is a way to explicitly say you want an integer, and you can specify the capital L suffix there. So for example, if you just enter the number 1 in R, that gives you a numeric object, but entering 1 with a capital L next to it explicitly gives you an integer. This distinction is not very important right now, but it will become important later. There's also a special number called inf, which stands for infinity. And inf is like a real number. It can be used in calculations, and you'll get the expected results. So for example, if you take 1 divided by 0, you'll get infinity. And if you take 1 and divide it by infinity, you'll get 0. So inf is a special number, and you can also have minus infinity too. There's another special value called nan, or nan, and this represents an undefined value, so you can think of it as not a number. So for example, if you take 0 over 0, that's not a number, it's not defined, so you'll get a nan back. Nan can also be thought of as a missing value, but we'll talk a little bit more about missing values a little bit later. So another thing that comes with each object in R is an attribute. So not every object in R necessarily has attributes, but attributes can be part of an object in R. Some of the most common types of attributes that we'll encounter are names, or dim names, for dimension names. Dimension, so a matrix will have dimensions. For example, it'll have a number of rows and a number of columns. If you have a multidimensional array, you'll have more than 2 dimensions. The class of the object, so every object will have a class. So for example, numeric objects, their class is numeric, and integer objects, their class is integer. Every object also has a length. So for a vector, it's quite simple. The length of the object is just the number of elements in the vector. And then there may be other user-defined attributes or metadata, so these are things that you can define separately for an object using various attribute functions. There is a general function called attributes, which allows you to set or modify the attributes for an R object. So once we start typing things into the R prompt, then we're going to start coding and doing calculations. So the things that we type into the R prompt are called expressions. So for example, the symbol which looks like a left-hand arrow and is actually the less than symbol followed by a hyphen, this is what's called the assignment operator. The assignment operator is what assigns a value to a symbol. So for example, in this first expression here, the symbol that I'm creating is called x, and the value that I'm assigning it is 1. And I use the assignment operator to create that. So x is 1 is an R expression. And the next expression, I'm going to print that value. So print is a function, and I'm passing it the symbol x. So when I print out x, I get its value, which in this case is 1. So another thing to think about is x is also considered is an R object that is a numeric object that has one element. So it's really a numeric vector where the first element is the number 1. In the third expression here, you'll notice I'm just typing x at the prompt, and when you hit enter, what happens is it prints out the value of x. So this is called, this is another way to print out an object without explicitly calling the print function. So in this expression over here, I'm creating a new symbol called message, MSG, and I'm assigning it a value of the string hello. All right, so now this is a character vector, and the first element of this character vector is the string hello. I could add other elements to this vector if I wanted to, but they would all have to be character. So the grammar of the language determines whether an expression is syntactically correct or not, or whether it's complete. So for example, if I just type x followed by the assignment operator and I don't type anything else, that's not a complete expression. And so when I hit enter, nothing will happen because it's waiting for the expression to be completed. The other thing I've got here is this hash symbol here. So this hash symbol here it indicates that everything to the right of that is a comment. And so the R engine will ignore anything that happens to the right of that symbol. So you can put things like comments or notes to yourself in code, and R will just ignore those comments. So once you've typed in a syntactically valid and complete expression at the prompt, when you hit enter, what happens is that the expression is evaluated by the R engine. And the result of that evaluated expression is then returned. And so sometimes when you evaluate an expression, nothing happens because there's nothing to really show. And so for example, in the first expression here, when I say x is assigned to be 5, so I'm creating an object called x. It's a numeric vector, and the first element is going to be 5. Now when I hit enter, nothing happens, and because there's really nothing to show. But now when I hit x and I hit enter, it prints out the value 5. So it prints out the value of x. So when I hit x, when I type in x and I hit enter, and it prints out 5, that's called auto printing. And so when you just type an object's name and hit enter, R will by default auto print the value of that object. This is the same as calling the print function on that object, which will just print out the value of that object. So you can explicitly print an object, or you can auto print an object. So this sounds a little complicated, but it's really just the natural thing to do, and it's what most people would expect. You'll notice that when I print out the object x, there's a little 1 in brackets here, and you might be wondering what that is. So all that indicates is that it's telling you what element of the vector is being shown. And this will make more sense when we have longer vectors to look at. But all this is saying is that the number 5 that you're seeing there is the first element of the vector. So for printing, you'll see that here I'm creating an object called x, and it's the sequence 1 to 20. So the colon operator here that I've used is what's used to create a sequence. So when I say 1:20, that creates a sequence of 1, 2, 3, all the way up to 20. So now when I auto print x in this case, you'll see I've got a much longer vector here. In this case, this is an integer vector. And you'll see that the first line of the printout has a 1 next to it because that's the first element, and then the second line has a 16 in brackets because that's the first element of that line is the 16th element of this vector. So it's all kind of straightforward, but just that's how the printout works. So the C function is another function that can be used to create vectors of objects, and you can think of C as standing for concatenate. Because it can be used to kind of concatenate things together. So for example, I can create an object called x by concatenating 0.5 and 0.6, and that will give me a numeric vector of length 2, where the first element is 0.5 and the second element is 0.6. In the second example here, I've got a logical vector where I'm concatenating true and false. So shorthand for true and false, you can use T and F, capital T and capital F. So these two lines give you the same object. You can create a character vector by concatenating a bunch of characters. You can create an integer vector by creating a sequence with the colon operator. And you can also create a vector of complex numbers where the I is a special symbol which indicates the imaginary part of the complex number. So using the vector function, you can also create a vector of a certain type and a certain length. So here I'm going to create a numeric vector of length 10. And by default, it will initialize the vector with a default value. And for numeric vectors, the default value is 0. So what happens if you take if you create a vector and you mix two different types of objects? And so the general rule is that R will kind of create the least common denominator vector. So it will not give you an error, but what will happen is that it will coerce the vector to be the class that's kind of the least common denominator. So here in this first example, I've gone from concatenating the number 1.7 and the letter A. So clearly these are not of the same class. One is numeric and the other is character. So the least common denominator here is going to be character. And so what you're going to get is that Y is going to be a character vector where the first element is going to be the string 1.7 and the second element is going to be the letter A. So in the second example here, I'm concatenating true, which is a logical, and 2, which is a numeric. And so what's going to happen here is that you're going to get a numeric vector, and the true is going to be converted into a number. And so how does that happen? And by the convention in R, true is represented as the number 1, and false is represented as the number 0. And so what you're going to get here is a vector 1, 2. Lastly, this last example here, I'm concatenating the letter A and the logical true. And so here the least common denominator, again, is going to be character. And so the vector that you end up with is the vector where the first element is A and the second element is the string true, so T-R-U-E. It's not going to be illogical. So you need to be a little bit aware of the types of coercion that can occur in R when you mix different types of elements in a vector. And because you won't get an error, but the coercion will happen behind the scenes. That in the previous slide we talked about kind of a implicit coercion that occurs behind the scenes, but you can explicitly coerce objects from one class to another using functions that usually start with the word as. So for example, if you want to convert something to a numeric, you can use a function called as.numeric. And if you want to convert something into character, you can use the function as.character. Now, if you apply these functions, so if you apply as.numeric to a numeric vector, nothing will happen. So here in this example, I'm starting off by creating an object called x, which is a sequence of 0 to 6. So this is an integer sequence, as you can see when I call class on the object. But I want to convert it into a numeric sequence. And so I can call as.numeric on x, and you can see that it prints out 0, 1 through 6, which looks like an integer object, but it's actually going to be numeric. Or I can convert it into a logical. And so I can say as.logical on it, and what happens? Well, as you can see, the convention is that 0 is false, and any number that's greater than 0 is going to be true. So here I've got, when I convert to logical, I get false, and then everything else is true. When I call as.character on x, it takes all the numbers and converts them into characters. So now I've got the string 0, the string 1, 2, etc. And finally, if I call as.complex, this is fairly straightforward because you can all it does is says that you have a complex number where all the imaginary components are 0. Now, coercion doesn't always work, and when it doesn't work, you get what are called NA values. So nonsensical coercion will result in NA. So for example, if I take the vector ABC and call as.numeric, well, there's really no way to convert the letters A, B, and C to numeric variables. And so what you'll get is a vector of NAs and plus a warning. Similarly, if you call as.logical on X, you're going to get a vector of NAs. Matrices are a special type of vector in R, so they're not a separate class of objects, but they're basically vectors that have an attribute called the dimension. And so the dimension attribute is an integer vector of length 2, where the first number is the number of rows of the matrix and the second number is the number of columns. And so if I can create a matrix, an empty matrix with the matrix function, and I can explicitly say how many rows and how many columns there are. This is not the only way to create a matrix, but it's one way. And so when I auto-print the matrix by typing the object M and hitting enter, you'll see that it'll show me that, first of all, the matrix is initialized with NA values, so there's no values in here. And you can see that there's 2 rows and 3 columns, and they're labeled by the numbers in the brackets. If I call the dim function on M, it'll give me the dimension attribute, which in this case it says there are 2 rows and 3 columns, because the first row is the number of rows, and the second number, the first number is the number of rows, and the second number is the number of columns. If I call the attributes function on M, you'll see it returns a list where the first element is the dim element, and it has the vector 2, 3. So these are all aspects of a matrix, which is a vector that has a dimension attribute to it. Matrices are constructed column-wise, so you can think of the matrix taking a vector, and all the numbers are inserted into the matrix by columns. So the first column gets filled, and then when you hit the maximum number of rows, then the second column gets filled, and the third column, etc. So if I create a matrix by taking the sequence 1 to 6, and then I specify that it has 2 rows and 3 columns, well, how does this matrix get constructed? So the way it gets constructed column-wise, so the first thing that happens is it takes 1, 2, and now there's only 2 rows, so it can only go to 2, and then that makes the first column. The second column is made up of 3, 4, and then the third column is made up of 5 and 6. You can also create a matrix by creating the dimension attribute on a vector. So for example, I can create a vector that's a sequence 1 to 10, and then add the dimension attribute to it. So here I'm using the dim function, but I'm assigning a value to the dim attribute of M. So here I'm assigning the vector 2, 5. So what I'm saying is I want to take this vector and transform it into a matrix that has 2 rows and 5 columns. And so now, after I've done that, I've got a matrix M, which has 2 rows and 5 columns, and it's filled in the matrix column-wise. Another way to create a matrix, and this is a common way, is by binding columns or binding rows. And so this is column binding and row binding can be achieved by the functions cbind and rbind. So for example, suppose I have the 2 objects, x, which is a sequence from 1 to 3, and y, which is a sequence from 10 to 12. If I cbind those 2 objects, then I'll get a matrix where the first column is 1 to 3, and the second column is 10 to 12. So this is kind of what you might expect would happen. If I rbind those 2 objects, then the first row will be 1, 2, 3, and the second row will be 10 through 12. So cbinding and rbinding is another way to create a matrix. The next data type I'm going to talk about is the list. Now I mentioned lists a little bit earlier in this lecture, and the idea is that they're like a vector, except that every element of a list could be an object of a different class. So that makes lists very, very handy for kind of carrying around different types of data. And they're very useful in R, and they become very common, especially when in conjunction with other types of functions that we're going to learn about. So here I'm creating a list called X, using the list function, which can be used to construct the list. And the first element is a numeric object of 1. The second element is a character, letter A. Third is a logical, and the fourth is a complex number. So this is not a problem with lists. And when I auto-print the list, you'll see that it prints out a little bit differently. It doesn't print out like a vector because every element is different. So you can see that in the double brackets here, so the elements are indexed by double brackets. So the first element is the vector 1, the second element is a vector with A, the third element is a vector with true, and the fourth element is a vector with the complex number 1 plus 4i. So lists are indexed. You'll notice that elements of the list will have double brackets around them, and elements of other vectors just have the single brackets. So that's one way to separate a list from other types of vectors. So a factor is a special type of vector which is used to represent categorical data. So, and there's 2 types of factors. There's unordered or ordered. So you can think of this as storing data that have labels that are categorical but have no ordering. So for example, male and female. Or you can have ordered factors which might represent things that are ranked. So they have an order but they're not numerical. For example, in many universities you'll have assistant professors, associate professors, and full professors. Those are categorical, but they're ordered. Um, you can think of a factor as an integer vector where each integer has a label. So for example, you can think of it as a vector as 1, 2, 3, where 1 represents high, and for example a high value, and 2 represents a medium value, and 3 represents a low value. So you might have a variable that's called high, medium, and low, and underlying in R it's represented by the numbers 1, 2, and 3. So factors are important because they're treated specially by modeling functions like LM and GLM, which we'll talk about later, but these are functions for fitting linear models. And factors with labels, generally speaking, are better than using simple integer vectors because the factors are what are called self-describing. So having a variable that has values male and female is more descriptive than having a variable that just has ones and twos. So for example, in many data sets, you'll find that there'll be a variable that's coded as 1 and 2, and it's not easy to know whether that variable is really a numeric variable that only takes values 1 and 2, or whether that variable is really, for example, representing gender, and the ones are males and the twos are females. But the problem is that's not something that's coded in the data set, so it's hard to tell. If you use a factor variable, then the coding for the labels is kind of built into the variable, and it's much easier to understand. So factors can be created with the factor function, and the input into the factor function is a character vector. So here I'm just creating a simple factor which has 2 levels, and the levels are yes and no. And so x is a factor, and you can see when it prints out a little bit differently from a character vector in the sense that it prints out the values yes, yes, no, and then it has a separate attribute which is called the levels. And so the levels of this factor are no and yes. Okay, so there's only 2 levels. I can call table on this factor, and it'll give me a frequency count of how many of each level there are. So for example, it'll tell me that there are 2 no's and there's 3 yeses. Now the unclass function strips out the class for a vector. So for example, if I call unclass on x, it'll kind of bring it down to an integer vector, and you can see that underlying the factor is represented as 2, 2, 1, 2, 1. So yes is coded as 2 and no is coded as 1. Now it's not really essential for you to know this because you can just treat the factor as being a vector of yeses and nos, but sometimes it's useful just to know underneath kind of how factors are represented by R. And so you can see it's really an integer vector with the levels attribute of no and yes. The order of the levels in the factor can be set using the levels argument to factor. And sometimes this is important because in modeling functions, when you include a factor variable, sometimes it's important to know what the baseline level is. And so the baseline level is just the first level in the factor. And the way this is determined in R is critical. It's determined using alphabetical order. So for example, if I create a factor variable with the elements yes and no, then the baseline level will be the first level that's encountered. And because no comes before yes in the alphabet, then no will be the baseline level and yes will be the second level. Now this may not be something that you want. You might want, for example, yes to be the baseline level and no to be the second level. And then in that case, you have to explicitly tell R that yes is going to be the first level. And you can use that using the levels argument to the factor function. So now when I print out the x object, you see that the elements are still the same. They're still yes, yes, no, but the levels attribute is reversed. It's because yes is the first level and no is the second level. So there's a special type of object that we haven't talked too much about yet, and these are missing values. Missing values in R are denoted by either NA or NaN, which we talked about before. NaN is used for undefined mathematical operations, and NA is pretty much used for everything else. And so there's a function in R called is.NA, which is used to test objects to see if they are NA, to see if there are missing values in that object. There's another function called is.NaN, which is used to test for NaNs. So NA values can have a class too. So you can have missing integer values, or you can have missing character values, or missing numeric values, etc. And so even though it looks like it's all NAs, the NAs can have different classes potentially. And then it's an NaN value is considered to be also Na. So for example, an NaN value, a NaN value is missing, um, is considered to be missing. So, but the reverse is not true. So an Na value is not necessarily a NaN value. I've got a few different types of missing values listed here. So here I created a vector x, which is 1, 2, Na, 10, and 3. So now this is a numeric vector, and the Na value in here is going to be a numeric missing value. So when I call is.na on x, what it returns is a logical vector. And the logical vector indicates whether each element of the vector x is missing or not. And so there's only one missing element in this vector, and so that's the third element. So you can see that the logical vector that's returned, the first two are false, the third is true, and the fourth and the fifth are false. So the element that's true indicates where the missing value is. If I call is.nan on this vector, you'll see that the vector that's returned is all false because there aren't any NaN values, there aren't any NaN values in this vector, so everything's false. Of course, if I create a vector that has a NaN value in it and an Na value in it, you'll see that is.na returns true for both of them, but is.nan only returns true for the value that's actually NaN. The last data type I'm going to talk about here is the data frame. The data frame is a key data type used in R, and it's used to store tabular data. So of course, tabular data make up a lot of what we use in statistics. Of course, not all types of data are tabular, but because so much data becomes a tabular form, data frames are very important in R. So data frames are basically represented as a special type of list, where every element of that list has the same length. Right? So you can think of each column of the data frame as an element of the list, and of course, in order to be a table, every column has to have the same length. However, each column doesn't have to be the same type. So the first column could be numbers, the second column could be a factor, the third column could be integers, the fourth column could be logicals. It doesn't matter what the different types are. So unlike matrices, which have to store the same type of object in every single element of the matrix, data frames can store objects of different classes. And so data frames also have some special attributes. The first special attribute is called a row name. So every row of a data frame has a name. And this can be useful for kind of annotating the data. So for example, each row might represent a subject enrolled in a study, and then the row names would be the subject ID, for example. However, sometimes the row names are not interesting, and often you'll just use row names of 1, 2, 3, etc. Data frames can be created by most often calling the read.table or the read.csv function, and we'll get into that a little bit when I talk about reading data into R. And you can also create a matrix from a data frame by calling the data.matrix function. Now you can't, if you have a data frame that has many different types of objects, and then if you coerce that into a matrix, it's going to force each object to be coerced so that they're all the same. So you may get something that's not exactly expected. So data frames can be created, besides using read.table or read.csv, you can use the data.frame function. And here I've created a very simple data frame where the first column is the foo variable, and the second column is the bar variable. The foo variable is an integer sequence from 1 to 4, and the bar variable is a logical vector with 2 trues and 2 falses. So when I auto print the data frame out, you'll see it prints out the 2 columns. And here the row names, since I didn't specify any special row names, it just defaults to 1, 2, 3, 4 because there's 4 rows. And then when I call the nrow function on x, I see that there's 4 rows, and the ncall function shows me that there's 2 rows. R objects can also have names. So this is not true for just data frames. It's true for all R objects. And this can be very useful for writing readable code and self-describing objects. So for example, I'm creating a vector that's an integer sequence 1 to 3, and by default there's no name. So when I call the names function on x, it gives me a null value. However, I can give a name to each element of the vector x. So for example, if I can say the first element is called foo, the second element is called bar, and the third element is called north. So now when I print out my x vector, I get a vector 1, 2, 3, but then each one has a name over it, which is the name I just specified. And so when I call the names function, I get the names that are associated with each element of the vector, foo, bar, and north. Lists can also have names. And so, for example, here I'm creating a list with the list function, where the first element is called A, the second element is called B, and the third element is called C. And so when I print out the list, it prints out the names of each element and the values associated with those names. Finally, matrices can have names. These are called dim names. So here I've created a matrix from the sequence 1 to 4. It's a 2 by 2 matrix. And when I use the dim names function, I pass it a list. Assign it a list where the first element of the list is the vector of row names, and the second element of the list is a vector of column names. So here I want to name the rows A and B, and I want to name the columns C and D. So that's what I pass to the dim names function. And now when I print out my matrix, I can see that the row names and the column names are labeled as I wanted. So that's kind of the whirlwind tour of the different basic data types in R. So far we've talked about the atomic classes, so numeric, logical, character, integer, and complex vectors. We talked about how vectors can only have elements of the same class, and the main exception to that is lists, which can have elements of different classes. There are factors, which are used for coding categorical data, both ordered and unordered data. There are missing values that are represented by NAs and NaNs. Data frames are used to store tabular data, where each column can be of a different class. And finally, all R objects can have names, which can be useful for creating self-describing data.